now. All right, so some other things about the exam. I have a page here called Sample Print Exam, and I added a new line here that I'll get to in just a minute. So when I'm writing an exam, I write just a whole bunch of problems from class, from the book, from homework down that I think you guys ought to know how to do, that I think you know, are show what we covered so far. Sometimes I break it down by topic. So here I'm explicitly stating, hey, here's the topic here. In past years when we met in person, I usually had a no calculator part. So you just did this, and when you were done with that, you turn it in and I would give you the part you can use a calculator on. But I have no control over that, so it's like all calculator if you want. But you got to write stuff down. You can't just write an answer. You have to have a justification for every single question. And so what does that mean? Well, sometimes it means not much, but sometimes it means you got to write a significant amount of work. So this practice one had, what, 25 questions? I wouldn't give an exam that long. That's unreasonable, but it's an excellent practice point. Let's see, what do we got in the chat? And the chat, as usual, has gone somewhere. Yeah, you can use any tool you want. You just can't use another human. So I'll talk about some tools so we're all on the same playing field, so that one person doesn't have more of an advantage than another because they got a better calculator. So that wouldn't be cool. All right, so you should definitely take a look at that. I'll do a couple problems off that practice one today for sure, and whatever else you guys ask me to. And then, so here's an example, the next page here, the previous exam, and it wants me to download it, fine. So this is the exam in 2018 my class actually took. So it's much shorter. There's some limits here that require, like the first one doesn't really require any work, nor the second one, but the 3, 4, and 5 definitely require a little bit of work or an explanation. And then there were some other harder limits where they got to use their calculator. So the first page, those were pretty fast, relatively easy problems. And then like this is a tough one. We'll do one of those today. Derivative at a point and derivative of a function. So, and that should be the end of it. Yeah, so in 2018, there were 13 questions, but some of the questions, like the ones on this page, like 1, 2, 3, and 4 were pretty easy. They take less than a minute, a few seconds each. And then I showed you what my work looks like. So there's another page here called Answers for that previous exam. So please take a look at these. It's in your best interest. And so like the first two, there really wasn't much justification. That's the limit. But the other ones, I show a little bit of work justifying my answers. So sometimes we justified answers with a table of values showing a sequence. Other times it was a wee bit of algebra or applying limit laws. And so for each of these, I have why I think the answer is what it is. And sometimes I had to write work somewhere else. And yours isn't gonna be a PDF like this. Again, it's gonna kind of look like the homework. So you'll have to write each problem down on paper. But this is the work I would expect to see on each of these problems. And like I mentioned before, sometimes the traditional limit approach is easier than the alternative. Sometimes the alternative easier. You never know until you do them both. So here I show both versions of that. All right, so again, you'll get a note from me when the exam is ready. It'll be an assignment in Canvas with a password. I'll give you the password, and then you can start it anytime. Like as soon as you get it, you can open it up and start looking at it, and it will be due tomorrow by midnight. And if you don't submit it by midnight, the system will submit it for you. And then I will grade. You won't see your grade till I go in and review all of the work and assign a grade. So unlike the homework where it grades it on the fly, the test won't do that. I have to grade each question. All right, so with that, are there any homework questions? Oh, calculator stuff. Okay, so Cole asked, can we use Desmos? Can we use GeoGebra? The answer is totally yes. Again, Desmos and GeoGebra both, they're similar but different. So either one works great. And then there are a lot of other software packages like I don't know if you ever heard of Wolfram Alpha. Alpha, it's a remarkable site for math and other stuff, science-y, and it can do all kinds of things. So you can type a question in here and it will do it for you. Now, if it looks like you just copied something from a place like Wolfram Alpha, it's usually fairly obvious to me compared to your other work. So please, just copying from a site like this is essentially plagiarism. So I expect you wouldn't do that, but it's a great tool for doing stuff. And the free version shows steps for some stuff, and then you got to pay if you want to see more. I have a nephew who went to school for engineering. And so when he was taking his math and science courses, I bought him a subscription for this. That was a few years ago. It was like $5 a year. I'm not sure what it costs now. But the pro version is pretty awesome. So if you're going to do lots of science and math stuff, this is something worth investing in my opinion. But I do not work for Wolfram Alpha, and I do not get any money from them. Put that out there. It's just a nice website. The free version I find is pretty sufficient for most stuff that you do, but it does do calculus. Other things that we'll look at later is there's a website called the Derivative Calculator. Derivative Calculator. And it does stuff like we're going to look at after the exam. So you could type in any kind of function you want here, like I don't know, 3 divided by, oops. 3 divided by parentheses x squared minus 5. And it says, hey, you want the derivative of this function? And I say, yeah, I'd like the derivative of that function. And then it'll whip through how one would calculate it. Now it uses shortcut rules that we're going to start covering on Wednesday. So this won't be all that useful for this test, except that it does state what the answer is there. But for this test, I expect to see work based on the definition of the derivative, which unfortunately this does not show. But it's a cool tool. It graphs stuff for us. It'll do second derivatives, and it's pretty awesome. So I will be using this with you later. I'll occasionally show you Wolfram Alpha stuff later. Yeah, so we're going to learn about things. So Kelsey asked about these rules, like a thing called the power rule. There's all these shortcut rules that we'll learn starting Wednesday, so that we don't have to apply that definition, because that definition's a ton of work. And there are patterns that develop that you can just see, oh, right, if it's this kind of function, the answer looks like that. And we will learn those rules, so we won't always have to apply the definition. So that's the goal after this test, is we're going to develop a whole bunch of shortcut rules so we don't have to use that definition all the time. Yep. And we'll get this big page of shortcuts. Kind of like, in trig, you came up with all those trig, what are they called? Formulas, all the, am I blanking? Trig formulas, I guess that's what they're called. And you just kind of memorize the formulas and use them where appropriate. That's what we're going to do after this stuff. All right, so I'm dying for a homework question from somebody. Anybody? Sure, we can do a continuity problem. All right. Okay, so Kelsey has a request for continuity, and Cole has one he wants to do. So I'll just wait for that in the chat in a minute, but I'm going to bring up an example to talk about continuity. Let's see, magic pen. So this is Calc 1, Exam 1 review. And I want to take a look at f of x equals the absolute value of x. And the reason I want to do that is by its very nature, the absolute value of x, we do different things depending on the input. So for example, if I plug in a number like 3, then the absolute value of 3 is 3. And that should be not a parenthesis. And if I plug in something like -5, then I do something different, right? The absolute value of -5 is actually 5. So the process that you take to make the calculation for absolute value depends on what you plug in. And that's a piecewise function, right? We look at the type of number and we decide what to do with it. So the way the piecewise thing works is the absolute value of x is just x itself if x is greater than or equal to 0, right? We get 0, absolute value is 0. If it's positive, the absolute value is the same positive number. Let's see, cool. Question number 5, in which section? The last one, 3.2? Yeah, okay, we'll get to that in just a minute. And then the way to describe what happened from -5 to 5 is basically I just took the opposite, right? The opposite of -5 is 5, and the way we take an opposite in math is we just put a negative in front of it. So technically, when we write something like -x, so when we write -x, we mean the opposite of x, and the way that's done computationally is to take -1 and multiply by x. So that's kind of the definition of what -x means. And so we take the opposite of x if x happened to be a negative number. So this is the definition of the absolute value, and we've all drawn the absolute value many times in our mathematical lives here. We know that it has this V shape like that right there, and there's the point 0, 0, and this part of the line over here, right, that part of the line is y equals x, and this part of the line on the other side, that's the line y equals -x on that side. So the absolute value of x is two other functions put together, is what I'm getting at up here. All right, now with that in mind, if we wanted to take the derivative of this function, we would have to apply the derivative to each part separately. So the derivative here would be a two-stage process. So I want to know, what is the derivative with respect to x of the absolute value of x? And so this is one way to write that. I want to know, what is this sucker right here? Now, Kelsey pointed the idea of continuity, and since these two pieces meet at the same point, this function is continuous. Continuous, missed the letter there. There we go. Exclamation point. It's definitely continuous. And continuity basically stems from any questionable point. And if the limit as x approaches that value, whatever it is, of the function, if it happens to equal the value of the function there, then this is in essence the definition of continuity. Now, if you look back at the definition, there were 3 parts to it. And the parts were, does this limit exist? Does the function value exist? And then the third part is, do those two equal each other? Right? So the definition for continuity was 1, does that limit exist? 2, does the function have a value there? And 3, do those things equal each other? And so if we look here at what's the limit as x approaches 0 of the absolute value of x, from the definition here, if we are on the right side, it can be evaluated at 0, and so we get 0. If we're on the left side, right, so if we're approaching this way here, so we're approaching, right, you can see as x approaches 0, y also approaches 0. Even though it's not defined there, for any x value as close as you ever get there, as x goes to 0, y is also going to 0. We can see that in the graph here. So the two-sided limit exists. So this is equal to 0. And we also know the absolute value of 0 is 0. So I meet all 3 conditions of continuity at this questionable point right there. All right, so another example of continuity is related to this derivative here. So let's do that. And remember, absolute value of x is a piecewise function. So it's equal to x if x is not negative, greater than or equal to 0. It's equal to the opposite of x if x happens to be less than 0, if x happens to be a negative number. And a quick sketch of that graph again. Comes in there and out there. So this is the graph of y equals the absolute value of x. Now, just a reminder about the derivative. So I'll do this in two different ways. Since this is a piecewise function, when I use the limit, I have to do a left-sided limit and a right-sided limit at 0. So we'll do that in a second. But remember what the derivative tells us. The derivative is a rate of change function. It tells us the rate of change of the function at a given point, which is the slope. And I think we can look at this and say, well, on the left side here, the slope is -1. And on the right side here, the slope is equal to +1. Okay. So if I were just going to take, so if I'm going to break this up into pieces, I would say, okay, if x is greater than or equal to 0, then I want to take the derivative with respect to x of x itself. And that would be the limit as x goes to 0 from the right, because of that part right there. I'm focusing on that top piece of just the function x. So that would give me an f of x plus h, which just is x plus h, minus f of x, which just is x, all divided by h here. And we can see the x's subtract out. H divided by h is 1, so I get a 1 here all the time, as long as I'm on the right side. Okay, and so that's getting to this slope on that side. If I go to the other side, if x is less than 0, then I have to take the derivative of x. Oops, ahead of myself. The derivative with respect to x of this other part here, because I'm on the left side, so I have to take the derivative of the opposite of x. And so this one is it's got a little extra there, so we got to remember to use parentheses when we plug in the x plus h. So that's going to give me the opposite of x plus h minus the function itself, which over here is -x. So careful when we use the formula. All over h. Oops, and I forgot to squeeze my limit in front. This time I'm approaching from the left side here. And if we clean this up here, what do we get? We get the limit as, and I got another typo, h goes to 0. As h goes to 0 on the left side. And so we have to distribute the negative there. So that's going to give me a -x minus h. Distribute the negative here, plus x all over h. Now in this case, I get -x plus x, so the x's go away, but then I get -h over h. So now I have to limit as h goes to 0 from the left of -h over h. And remember I mentioned earlier, a negative just means multiply by -1. So h over h is 1 times -1 is -1. Everything's gone, so the answer is just going to be -1 there. So I get the -1 on the other side. Now, we just made a new function here, right, for the derivative. And so I'm going to write that down on a new page. The derivative with respect to x of the absolute value of x, it's equal to 1 if x is greater than or equal to 0, and -1 if x is less than 0. So that's my new function. Let's graph it. So let's say here's 1, here's -1. Let's do it in green. So let's see, it's 1 if x is greater than or equal to 0. So I get exactly 1 all the time out that way. And at 0, I get 1. Here, at -1, when if y is -1, x can't be 0, but we get right up to the edge of it. So that's an open circle that way. So for any x value on this side of x equals, any x value on this side of x equals 0, I get -1 for the y value. If x is positive, I get +1. And notice we have a break here. So if I take the limit as x goes to 0 on the right side of this function, let's call it g of x. I'm on the right side, so the answer is 1. If I take the limit as x goes to 0 on the left side of this function, the answer is -1. So if I try to evaluate the two-sided limit, if I just say, hey, what's the limit when x approaches 0? I don't care which side you're on. Since the sides don't match, then this does not exist. And since that does not exist, then this function is definitely not continuous at 0. Not continuous at x equals 0. But it is continuous everywhere else, because any other point I pick, like this one right here, it doesn't matter whether I'm approaching from the left or the right, I'm always going to get 1. Over here for that point, it's continuous at that point, because as I approach from either side, it's approaching that point. All right, so let's see, Cole 3.2, question number 5. Let's take a peek. And reminder, there is an interesting talk going on Thursday the 28th at 2 p.m. I'm going to be checking that out. That looks like fun. Three, 2, homework number 5. Oops, wrong button. Sure. Okay, so we got, mine looks like 4x squared plus 2. Was yours something like that one, Cole? Yeah, okay. And here I'm recommend doing it in parts here. And I don't actually ask for the limit, but we'll take it a step farther and do that. So these are the parts in using the traditional definition. So mine's 4x squared plus 2. New page. 2, number 5 like, and I have f of x equals 4x squared plus 2, and I want to find the difference quotient using the traditional approach. So difference quotient, which is f of x plus h minus f of x all over h. And when I did this in class over the past week or so, I said that I recommend a 3-step process for complicated equations, where you first find that, then you find the difference, and then third you divide. And so that's what I asked to do for this particular question. Whenever you're finding f of x plus h, my recommendation was think of your function as just a place to put stuff, right? So I just plug stuff in where there was an x. So I'm going to rewrite the function with parentheses where there was an x. And then what do I want to put in there? Well, I want to put where there was an x, I want to put an x plus h in there. So that's how I get it set up right. Following that, I got to realize that there isn't a shortcut for squaring something. That means I have to multiply it by itself. So that would be my first step now that I have the x plus h plugged in. So x squared, and then we're going to get an xh plus another xh. So that's 2 xh's and then an h squared. And so now I'm ready to multiply by the 4 and then add the 2. So distributing the 4 through there, I get 4x squared plus 4 times 2 is 8xh plus 4h squared plus 2. So let's see, I think I did that right. And I had already simplified this part above, nothing much changes, so that would be my first answer right there. Then I need to subtract f of x. So now I want to know what is that f of x plus h that I just calculated minus f of x. So that's going to be that 4x squared plus 8xh plus 4h squared plus 2. And then from that, I want to subtract the original function, put it in parentheses when you subtract something to be careful, 4x squared plus 2. So both the 4x and the 2 are being subtracted. So when I do that, I'm going to get this 4x minus that 4x, so they're gone. And I'm going to get 2 minus 2, so they're gone too. So all that's left from this part is 8xh plus 4h squared. If you have a question as I'm going through this, please jump in the chat or voice, hey Parker, what's up here? How's it going so far? You're starting to figure out what went wrong before? Okay. So let's do the last part. We divide by h. So I'm gonna have to go to a new screen, or I guess I can squeeze it over here. Let's block this off. So part 3 is where we do that division. So we've cleaned up this difference right here. And now we want to divide that by h. So my difference ended up being the 8xh plus 4h squared. Now I'm dividing that by h. And the secret here to being safe is to ask yourself, can you factor the numerator? And it turns out you could factor an h out of the top. You could also factor a 4 if you wanted to. And so I'm going to do that. I'm going to factor out a 4h from the top. 4 goes into 8 twice. The x is still there, but I took the h. Plus, I took the 4 and one of the h's, so there's just an h there. And then I can say, all right, I've got this h divided by h here, and a number divided by itself is 1. And so that's going to leave me, the 4 is still chilling there, times 2x plus h. And so this would be the answer for the third part. And I have it in factored form, but I could also enter what 8x plus 4h would work also here. Good question. All right, let's see, what else should we do? Other homework problems, I'm going to pick something challenging from the practice. Let's see, here's the practice. Yeah, delta epsilon, good call. All right, so I'm going to do one similar to number 17 on the practice. Okay. All right, so this is the precise definition of the limit. And we're going to take a look at f of x equals 2/3 x minus 5. And we're going to let a equal, how about -3? Let's make it interesting. And so I believe that f of -3 is equal to -7. And so that's what I think L is here. And what I want to do is I want to find delta for any value of epsilon. So sometimes I'll say, hey, let epsilon equal 1,000,000th or 1,000th or 100th, figure out what delta should be. So here I'm going to do the more generic version. I'm just going to say, hey, epsilon is just some small number, find delta. And just to, actually, I'll do this and then I'll explain the intuitive meaning of all of this. So I think that the limit as x approaches -3 of 2/3 x minus 5 is equal to -7, and I want to be able to find a delta given an epsilon, and epsilon is just going to be epsilon. So the way that works is we take the end result that says the difference between f of x and L. So how far are those guys apart? They have to be relatively close. Epsilon is that small number. Okay. And then we want to end up with x minus a is less than delta. Some days my deltas come out a little screwy. That's a nice delta right there. So I plug into this, and then the goal is to make this thing on the left look like this thing on the right. So goal. All right, f of x is 2/3 x minus 5. So I have 2/3 x minus 5. And then I want to subtract from that the limit, which is -7. Be careful with your signs. And that has to be less than epsilon. And then we apply some algebraic trickery to make this look like that. Okay, so let's see, I might as well deal with that. So -5 minus -7 is -5 plus 7. So this gives me 2/3 x plus 2 in the absolute value. And oh, note about my a here, my a is -3, so let's write down the goal. So x minus -3 is going to look like x plus 3 in absolute value. So my goal is to get something that looks like this from this over here. Okay, so this 2/3 is clearly in the way. So to get rid of that, what I'm going to do is I'm going to multiply both sides by 3/2. And so if I distribute the 3/2 through here, what do I get? Well, 3/2 times 2/3 is 1x. And since this is a positive number, I can bring it into the absolute value. So that gives me an x. And then 3/2 times 2 is just 3. And bang, there's my x plus 3 that I was hoping for from the precise definition. And then on the other side, I get 3 times epsilon over 2. And so that right there is going to be my choice for delta. So delta should be 3 times epsilon over 2. And then I'll get close enough. All right, so what's the point of all of this? Let's look at a picture. So a delta epsilon precise definition is basically a kind of a dare. So let's see, what were my numbers again? -3, -7. So let's say -3 is over here, -7, maybe that's down here-ish. So here's my point of interest. And my equation was 2/3 x minus 5. So -5 would be about here-ish. So that's -5, -7, -3. So this is my line through there. Oops, accidentally moved the other line. Okay, close enough. So there's my line, and so we have x equals -3 leads to y equals 7. And basically what someone says is, all right, you think the answer is -7, What I need you to be is close to that. So the distance away from -7, so I want to be within, let's say epsilon equals 1/100th of -7. And then you have to guarantee me that you can find x values so that when you plug any of those x values in over here, you get close enough for what I said the margin of error is. So this is like a margin of error. Okay, so I say you have to assure me that your results are within 100th, or maybe I come back and say within 1/1,000,000th. And wherever you start, the end result has to be close enough. Otherwise, everything's going to go to hell, right? Maybe we're building a bridge from 2 different sides and we have to make sure they meet, right? Maybe we're building a rocket and we have to make sure that, you know, the trajectory works out right. So we can't do anything perfectly in reality. There's always margins of error. And this is about having a starting region to work with and ending up within a reasonable tolerance at the end. And this epsilon here is what somebody defines as a reasonable tolerance. That's the point of this definition, that we can ensure that we're always going to be within that reasonable tolerance. And in this case, yeah, as long as whatever you say the tolerance is, you know, as long as I start within this range. So for example, for these numbers right here, if that was epsilon, then I would say, okay, delta should be 2/3 of that, or was it 3/2? It was 3/2 of that. Which would be what, 0.015. So the absolute value of x minus -3, as long as that's within 0.015, what does that look like? Well, this number right here is always the midpoint on the number line, right? Like I've drawn there, -3 is in the middle. And then x has to be within 0.15. So I could go 0.015 to the right, or I could go 0.015 to the left. And as long as x is in that interval there, I'm cool. So x could be over here at what, -2.985, or x could be over here at -3.015. And as long as we pick one of these x values in this region, then I'm assuring the y values will be within 0.01 of -7. All right, tomorrow's class be more review. I am not moving on to anything new tomorrow. No, according to the schedule, tomorrow's the exam. So if you guys want to do more review tomorrow, we can. Yep. And I also have office hours today at 10 and 2, and office hours tomorrow at 10 if you need more time to play around with me. All right, let's do another problem. That square root's a good one. That one's cute. So is number 24. So what do you think? The square root or the rational one? 23 or 24? 23 it is. Okay, let's try it. So, oops, I got a page when I need it. I want to know if f of x is equal to square root of 25 minus x. Did I copy that correctly? Yep. What is f prime of x? So we have two choices. We could use the traditional x plus h approach, or we could use the difference of x and a, the alternative one. And off the top of my head, I think they're probably about the same, but I have a request there for the alternative. Thank you, Kelsey. So the alternative says find the limit as x approaches a of f of x minus f of a divided by x minus a. And here we weren't given a value for a, so a just stays as a. So let me just double check that I'm not lying. Yeah, so this is the general derivative section. So a is not a number. Well, it is a number, I just don't know what it is, so I'm calling it a. So what does that look like? Well, in this case, I'm just gonna write it all out. Usually about the alternative, I don't break it down into steps. So f of x is just right there, square root of 25 minus x. F of a is just the square root of 25 minus a. And then the bottom, I just simply have x minus a. Usually when you have square roots floating around, you use the idea of multiplying by the conjugate. So what I'm gonna do is I'm gonna multiply by the conjugate of that, top and bottom. So that would be the square root of 25 minus x plus the square root of 25 minus a. And the cool thing about multiplying by a conjugate is that the middle terms disappear in the numerator here. All right, so the numerator, so again, conjugate is using the fact that a minus b times a plus b equals a squared minus b squared. So now I get the square of the square root of 25 minus x, which is just 25 minus x, minus the square root of 25 minus a, which is just 25 minus a. And I'm using parentheses because I don't want to mess up my signs there. In the denominator, I just have x minus a, and I'm not going to multiply these guys out. Usually we leave the denominator alone. All right, and again, we're working on the limits. And let's see, what do we got? We got to distribute here. So that's going to be a negative 25, and then that's going to turn into a positive a. 25 minus 25 goes away, which is kind of cute. And I end up in the numerator with a negative x plus a, which I could flip and write it as the opposite of x minus a. And I'm going to write it that way because I have an x minus a in the bottom. And I'm ready to take the limit, almost ready to take the limit of all of this. Thing to note here is I have a number divided by itself. And whenever you have a number divided by itself, you get a 1. So there's a negative 1 in the numerator now. In the denominator, I only have that left. And so the numerator evaluates to negative 1 because there's no x's there. In the denominator, x is going to a, so that x becomes an a. So I get the square root of 25 minus a plus the square root of 25 minus a. And so we can clean that up a little bit by saying, hey, I've got 2 of these guys on the bottom. And then we just replace a with an x. Okay, so here's what I think we have. We tried to take the derivative with respect to x of the square root of 25 minus x. And it looks like we get negative 1 over 2 times that square root, 25 minus, and I'm going to put an x here now instead of an a. Cool. How do we know it's right? Good question. We could plug it into a derivative calculator and it would just say, hey, the derivative of this is that. Or we could plug it into Wolfram Alpha, or we could go to Desmos or GeoGebra, pick a number and see if a tangent line works there. But we are just about out of time for fun with math. It's 9:49. I'm going to end on time for once. Sorry, I'm time challenged. I'm good at math, but not with time. I keep thinking someday I'll get better at it, but hasn't happened yet. Okay, so later today you'll get a message from me that says, hey, the exam's ready to go. Here's the password. Start it whenever you want. It is due tomorrow by midnight. I have office hours today at 10 and 2. There's a link in the syllabus to my office hours. And then I have office hours tomorrow at 10. And I will be online at this channel at 9 o'clock tomorrow if anybody wants to ask more questions. The only thing I can't do for you is if you ask me to do a test question, right? I obviously can't do that, but I'm sure you could find a homework question that's similar to a test question, and I could go over that with you. So take care, do good math, be safe in the slick, snowy weather out there. I'll see you soon.